Hi students, in the continuation of the previous two lectures in which we were discussing the pipelining in the computers, today we will discuss the data hazards in the pipelining. As in the previous two lectures, we have already discussed that what is the pipelining, why it is required in the computers, and what are the advantages and disadvantages of the pipeline structure over the unpipeline structure. We have already discussed that the pipeline structure is having some hurdles, which are also called as hazards. There are three types of hazards, and these hazards are called structural hazard, data hazard, and control hazard. So today we will discuss what is the data hazard and what is the impact of that data hazard and how can we remove the data hazard in the pipelining for the smooth functioning of the pipelining. So the data hazard. What is the aim of the pipelining? The aim of the pipelining is to change the relative timing of the instructions by overlapping their execution. If we will look at the unpipelined structure, then we will find that the sequence of execution of the instruction will be second instruction will only start after the completion of the first instruction unless the first instruction will not complete its execution, the second instruction will not start. But similar thing will not happen in the case of pipeline structure. In the case of pipeline structure, during the execution of the first instruction, the second instruction will start its functioning. So that is why it is called overlapping of the execution of the different instructions. Okay, so due to this overlapping in which one part of one instruction is performing different operation, and at the same time another part of the another instruction is going to perform the another operation. So due to this, the data and control hazard will occur in the pipelining. So how we will be able to understand the data hazard? The data hazard occurs when the pipeline changes the order of read and write access to the operand, so that the order differ from the order seen by the sequentially executing instructions on an unpipelined machine. So if we will look at this example, now we will try to understand the data hazard in detail with the help of one example. Let's suppose we are having one program. This is a one program. The different instructions are there. 5 instructions are there in this particular program. The first instruction is add R1, R2, R3. The role of this instruction will be to add the data of R2 and R3. And after the addition of R2 and R3, the result will be there in R1. The second instruction will perform the operation. What it will do, it will perform the subtraction operation on R1 and R5, and whatsoever the result will be there, that will be moved to the R4. And again, the third instruction will be used to perform an logical operation and bitwise logical operation of R1 and 7 will be performed, and whatsoever the result will be there will be stored in the R6. And next OR, it will perform the OR operation, and next will perform the X. This is the actual sequence of execution of the instruction. But in the pipeline, the smooth functioning will not happen, because in the case of first instruction, the result will have to be stored into the R1, and whatsoever the result will be generated after the execution of the first instruction will become the operand or input for the rest of the instructions. So this particular situation will create the hazard for the rest of the instructions. Unless first instruction will not prepare the result, the second instruction cannot start its execution, because the R1, the data of the R1, which will be the outcome or the result of the first instruction, will have to become the input for the second instruction. So second instruction or second onward instruction will have to be waited for the result to be prepared by the first instruction, until unless the first instruction will not prepare the result, final result, and store it into the R1 register, next instruction cannot perform the execution, because in the next instructions R1 is going to be act as one of the operand to perform its operation. So now we will try to understand with the pipelining structure. The first instruction add R1, R2, R3 will be fetched in the first clock cycle, as we know that as per the functioning of the pipelining, or as per the operational sequence of the pipeline structure, the first instruction will have to be fetched in the first clock cycle. In the second clock cycle, the first instruction will have to move to the decoding stage, and upcode of the second instruction will be fetched. In the third clock cycle, the first instruction will move to the execution unit, and second will move to the decoding part, and the third will automatically be fetched from the memory. During the fourth clock cycle, after the execution, if the data will have to be written into the memory, then the first instruction will perform the memory access operation, and at that point of time second will start its execution, and third will move to the decoding, and fourth will be fetched. And in the fifth clock cycle, the first instruction will write back. If the requirement of the instruction is to write the result to any register, then it will write back to the register. Second will perform the memory access if it is required. Third will execute. Fourth will decode, and next one more instruction will be fetched from the memory during the fifth execution. If we look at this, the things looks like very easy, but what will happen actually? As we know that during the decoding part, the second instruction required the operand R1 and R5. It can be sent to the next execution stage for the execution. If the processor will read the data of the R1 in third cycle, at this point of time the data is still not ready in the R1, because the data in the R1 will be ready after the completion of the fifth machine cycle in write back cycle. So unless the data will not be finalized by the first instruction, the actual required data will not be stored into the R1. Even if the second instruction will read the data of R1 and will try to execute it, then that will be the wrong result, because till this point whatsoever is the actual requirement of the input data is not still ready. So that is called data hazard. So data hazard arises due to what? The unavailability of the operand required for the next instruction. So here in this case, this instruction, second instruction, required the data of R1, but still the data is not available. Similarly, in case of third instruction, the data is required at the fourth cycle, but still data is not ready. Data in the R1 will be ready after the completion of fifth machine cycle. So what is the data hazard? The data hazard, the situation of the data hazard occur when the required operand, whatsoever the operand is required for the next instructions, is not available, or it depends upon the outcome of the previous instruction. Then next instruction will have to wait till the data will not be ready for that particular instruction. So in this particular slide, we will try to understand the same concept along with the data path. So we will try to understand the operation and where the hazard will occur. Here is a one program which is written, the different instructions are there for this particular program, and R1 is a one operand which is required for every instruction. And in the first instruction, the whatsoever the result will be available after the execution of the R2 plus R3, that will move to the R. So now we will try to understand what will happen after the execution of each and every clock cycle. All the instruction after the add instruction use the outcome of the add instruction, that is all the instruction after the addition instruction, after the first instruction, will have to use the data of R1 as a one of the operand to perform its operation. But what will happen? The add instruction will actually write the data, will actually generate the data for R1 in write back cycle, and that particular cycle will be the fifth cycle of the pipeline. This one. Actually, the data will be available within the R1, whatsoever the updated data that will be available within the R1 after the completion of the fifth machine cycle. But what is the requirement of the second instruction? Sub instruction required or needs R1, the data of the R1 in the third cycle. The data hazard will occur. It will occur by why? Because if it will read the data, whatsoever the data is present within the R1 and will consider it as the required operand, will gives us the wrong result. So that is why the hazard will occur over here. Similarly, for the AND operation as well, if the instruction will read the data during the fourth cycle, then again it will create the problem, will gives us the wrong result. Okay, now we will move to the OR operation. So what will happen? What is the requirement in OR operation? Again, for the fourth instruction, which is the OR operation, in this particular case, no hazard will be there. Now you can ask the question. Till now, no data is ready. As you have already said, the data will be available after the completion of the fifth machine cycle, and at the same time, ID is required the data in the fifth machine cycle as well. But if we will look at the previous lectures, then we will find that the reading and writing of the registers will have to be done in the same cycle. That particular cycle will be divided in two halves. In the first half, a write operation will be performed. Whatsoever the write operation is required for in that particular cycle will be performed, and reading operation will be performed in the second half. You can see this. Half register block is represented with dotted line and other is represented with line. Okay, this particular portion is representing that the write operation during the half cycle of the clock cycle number 5, processor will perform the write operation, and during the second half cycle of the fifth machine cycle, processor will perform the reading operation. So that is why even if the data of the R1 will be available after the completion of the fifth machine cycle, but due to this functionality, the data will be available after the completion of half cycle of the half of the fifth cycle. So as soon as the data will be written to the R1, just after that processor can read the data of R1, and in this particular case there is no hazard. So hazard will be there, hazard will be occur for the second instruction in which data is required at this point of time. In this half cycle it will have to read the data, but still data will not be available. It will be available at fifth cycle. So this is the hazard, and for the third instruction there will be also hazard. Again the data is required at the fourth cycle, but data will be available after the completion of the fifth cycle. So data hazard occurs for the two instructions, subtraction instruction and AND instructions. So there will be no hazard for the OR operation, and there will be no hazard for the XOR operation. As for the XOR operation, the data is required in the sixth cycle. So till that, data of the R1 will be available. So there will be no problem. There will be no hazard to read the data of the R1 in the sixth cycle. So in this particular example, in this particular problem, there will be hazard for the instruction number 2 and instruction number 3. Okay. So in this particular diagram is showing the details of the occurrence of the data hazard, and as we have already discussed that the result will be ready after the completion of the fifth machine cycle, but the data is required for second instruction. Data of R1 is required for the second instruction during the third clock cycle, and data for third instruction is required for the fourth cycle, which will not be available. So in these two conditions hazard will occur, and again we can see that for the third instruction OR, data will be ready after the first half of the fifth clock cycle, and data can be read by the fourth instruction during the second half of the fifth cycle. So there will be no hazard in this case, and again there will be no hazard for this case. So hazard will occur for these two cases. So this particular slide is showing the detail of the occurrence of the data hazard for this particular example if the program will be written in this form. Okay. The condition can become more complex if we will write the instruction sub r1 comma r1 comma r5. Then what will happen in that particular case? No doubt r1 is the operand in that particular case, but the result will be stored in r1 as well. So in that particular case, hazard will be there for the rest of the stages as well. Okay, so that is why the pipelining or the execution of the pipelining is not that easy as we can predict. It looks like very easy. Now, what will we do? Whenever hazard will occur, as we have already discussed during the discussion of the structural hazard, the hazard will be replaced with the stall or bubble, whatsoever we can call it. So in this particular example, how many stalls are required to avoid the data hazard in the program? We will try to calculate it. As per our discussion till now, this ID instructional decoding is not possible in the third cycle. Is not possible in the third cycle, as data for the R1 is required, but data of the R1 will at least be ready within the first half cycle of the fifth machine cycle. So we will have to introduce the two stalls for third and fourth machine cycle and extend the operation for the second instruction to the fifth stage. So in the fifth stage, first half will prepare the result in R1 and processor will read the operand of the R1 in the second half. So two stalls are required to be introduced in the sequence of pipelining, and naturally if the stall will be introduced over here for the third and fourth machine cycle, then the operation of each and every instruction after this instruction, because this will become the affected instruction. So as we have already discussed that even if we will introduce the one stall in any instruction, then whatsoever the instruction will come after that particular instruction will automatically be shifted, or one stall will automatically be inserted to all the next instructions. Okay, as we have already inserted the two stalls for third and fourth clock cycle, so naturally the fetching of the third instruction will be delayed by the 2 cycle. So the fetching will be happen in the fifth cycle instead of third cycle. Okay, so the pipelining or the number of stalls which will be introduced in the pipelining due to the non-availability of the result or due to the data hazard will be 2. So if we will introduce the 2 stalls, then data hazard can be avoided. This is the one way. Now, is there any other solution, or we will have to install or introduce the stalls for every execution? Do we have any other set of solution with us? Yes, and that is called data forwarding. Stalls can eliminate by introducing some sort of hardware techniques which are called data forwarding or data bypassing. Okay, so now we will try to understand what the data bypassing is and what is the data forwarding. So the solution to the data hazard is, as we have already discussed, that the solution to the data hazard is the data forwarding. Now we will try to understand what is the data forwarding and when and how data forwarding will be able to remove the data hazard. Okay, so what will be the working of the data forwarding to remove the data hazard? To remove the data hazard with the help of data forwarding, the designer will take the advantage of the whatsoever the functioning of the pipelining is. So now we will try to understand what is the functioning of the pipelining. As we know that the result, whenever the result will be prepared by the ALU and after the execution of the arithmetic and logical operation, the result will be stored into the EX memory register. So as we know that latches and registers are available in between the two different stages. which are used to store the data of the different stages of the pipelining. Just like this. This is the what? A set of registers are there which is used to store the data and control signals of the first stage, and similarly this is another set of registers which are also used to store the data of the second stage. Similarly, this stage is also there which is used to store the data of the third stage, and so on. This we have already discussed in the previous classes when we discussed what is the need of the extra hardware for the pipelining, or how a unpipelined structure can be converted into the pipeline structure. So by taking the advantage of this, as we know that after the completion of the execution, or after the completion of arithmetic and logical unit, the data will be stored, or result will be stored in the X or memory access set of registers, and will be available with the ALU latches as well. This is the one. What will we do if the forwarding hardware, the extra hardware which we will introduce over here to forward the data, that is called the forwarding hardware. If the extra hardware which is known as the forwarding hardware detect that the previous ALU operation has written the register corresponding to a source for the current ALU operation, if forwarding hardware will be able to detect the moment ALU perform its operation and will write the result to the corresponding registers. For example, say after the completion of the third cycle, result will be ready within the ALU and that will be stored within the latches. But in actually this executed result which is ready after the third stage, but due to the sequence of event of the pipelining, the data will be written in R1 after the completion of fifth stage. Data will be ready within the pipeline structure after the completion of third, but it will be written to the actual destination after the completion of fifth machine cycle. So we will have to do what? We will have to bypass this these two stages on the need basis with the help of forwarding hardware, which will detect once the data will be ready or the arithmetic and logical operation will be completed. Then what it will do, it will bypass these stages and will directly supply to the next stage. Okay, so we will try to understand this. So this data forwarding will do what? In the forwarding hardware detect, if the forwarding hardware detect the previous ALU operation has written the register corresponding to a source for the current ALU operation, what the control logic will do, it will select the forwarded result, whatsoever the result will have to be forwarded to the destination after the completion of fifth machine cycle as a ALU input rather than the value read from the actual register file. So what does it mean? The forwarding hardware will read the result from the ALU registers rather than it will read from the R1 register. Okay, so this is the solution which is called the data forwarding of the to avoid the data hazards in the pipelining. So this is the discussion which is written over here. The sub instruction will not use the R1 until the data will not be written in the fifth cycle. Add instruction will generate the result of addition R2 plus R3 in the execution or memory latch register after the completion of third cycle. As we have already discussed that the execution unit will actually generate the result and will store to this particular latch whatsoever the latch will be there in the data path, because this is not a detailed data path, so we cannot see that particular register. In the next slide we will to see that sub instruction need the result of add in ALU as an input before the fourth cycle. So in this particular we will see this is the first instruction. As per its normal execution, the data will be written in the R1 after the completion of fifth clock cycle. But in actual practice, the data will be ready because the arithmetic and logical operation will be completed within the third stage and will be stored over here in the latches. And this particular latch is called execute / memory latch, because it is in between it is a latch or it is a set of registers which will be in between execution stage and memory access stage. Okay, so the data will be ready after this. So what will we do? Our data forwarding hardware will do what? It will read this data from this latch and will directly supply to the ALU, rather than this will be read from this register and will come back to this. What it will do? It will directly read the data from this latch and will supply to the second instruction. So hazard will be removed. In the fourth machine cycle, we required, or the second instruction required the data to execute it. What it will do? It will directly fed to the one of the operand to the input of the ALU for the sub instruction. So the hazard for the second instruction will be removed, and as we can see that whatsoever the data will be available over here will have to proceed to the next stage. And as in this particular instruction there is no need to access the memory, so it will not go to the memory, it will directly go to the next stage, and it will again be stored after the completion of the fourth machine cycle at the latch of this memory access latch. And from there the data forwarding hardware will directly supply the R1 operand to the ALU for the third instruction. Okay, so again the data hazard will again be avoided with the help of data forwarding. So it will bypass this stage and directly supply the data to the ALU. Okay, but for the third instruction, or there is no need to insert any forwarding hardware, because the data will automatically be loaded or to the registers R1 during the first half cycle of the fifth cycle, and processor will automatically read it in the second half of the fifth clock cycle. So there is no as we have already discussed, there was no hazard in this particular case, so there is no need to bypass it. There is no need to introduce any data forwarding hardware. Okay, so this is how can we eliminate the data hazards, and how can we achieve the data forwarding. Thank you.